Hello and welcome. My name is Matthew Dillman. I'm a student in MA 366, which is Ordinary Differential Equations, and today I'm going to be walking through my honors project. Um, so before I start and dive in and derive all these equations and do a bunch of math, I'm going to start by kind of summarizing the objectives of the project and as to kind of the motivation for why I did this. So the first objective of the project was just to explore some model. Explore some model. Right? So I'm going to take some real world physical system and then be able to explain this in some sort of mathematical way. And in particular, I would like to derive some equations of motion. And I'm going to say that's EOM, equation of motion, and then be able to solve, and I'm going to put that in air quotes, and be able to solve that equation, right? We know the differential equations are pretty complicated at times, so being able to solve them depends on what you define solve to be, right? Does that mean analytically, numerically, right? Graphically, right? There's all kinds of ways. But just somehow get some solution curve is the goal, basically. And then the third objective is to interpret the result. So interpret the result. So I want to have some real life system, some real life situation, have an equation, solve the equation somehow, and then interpret the solution. That's kind of the goal of this particular project. Okay, so I'm going to start first by some sort of motivating example, say. So let's say I have a ceiling, not very interesting, but it's fixed. So basically that's what the angled bars or lines mean. That it's just the ceiling is fixed in place, it's not going to move during this particular motion. But what is going to move is this particular block with mass m, right? And this is going to be suspended by a spring with spring constant k and a damper with damping coefficient mu. And then it's going to be in a gravitational field. So say it's going to be on Earth, right? So there's going to be a force due to gravity, right? There's acceleration due to gravity, which is the force due to gravity acting on the block. Okay, great. So this is the particular setup here. First, I'm going to say that we're in equilibrium. So at some distance L from the ceiling, we're just going to be kind of sitting there in equilibrium. And that's kind of the case here, right? And then now we're going to do is suppose that I kind of displace this a little bit. So I'm going to call this mu. If I have some sort of initial displacement, if I pull it down a little bit, or if I push it, right, with some velocity, the spring, right, and the damper are going to exert forces on this particular block, and it's going to move, right? And the equation of motion of this, which should be reminiscent from this class, is going to be mu double prime plus mu times mu times u plus ku prime equals 0. Okay, so this is the equation of motion for this particular system. And we know that the solutions to this particular differential equation here is usually in terms of sines and cosines. That's the idea, right? Depending on that damping coefficient mu, right, they could potentially just be exponential terms, right? Basically on the order of exponential, like just exponentially decay to 0. But that's kind of our understanding of this. So it's going to oscillate up and down with this particular setup here. Okay, so that's not very interesting. We've already done a lot of that for this particular class. So now what I'm going to do is I'm going to change it a little bit. I'm going to change the situation. So I'm going to have, once again, I have the same fixed ceiling. I'm going to have the same spring with a spring constant k. I'm going to draw that a little better. And I have the same damper, mu. Now, instead of a box, or instead of a block, sorry, I'm going to have a box. So I'm going to draw like this. Oof. Okay, I'm not the best artist in the world, okay. And inside this box, I'm going to have sand, okay. And the actual material inside doesn't really matter. But I'm going to have some sort of maybe granules of particles, or maybe like packing material or something, or water. I don't know. It doesn't really matter what it is, but just something inside of it that has some sort of fluid-like properties, basically. I don't know the idea. Okay, so I have sand in here, and I'm going to call this particular setup here, once again, I'm at length L. So in equilibrium, I'm going to call this mass at this particular state m0 or m0. So once again, it's an equilibrium, nothing very interesting is happening. Now I'm going to say that suppose a long time passes, so it's sitting here in equilibrium, just not doing anything. But as time passes, right, these particular walls of the box are, say, thin, So like imagine like a cardboard box or something, right, with thin walls. Then over time, the sand is going to start kind of slipping through the cracks, say, of that cardboard box, right? It's going to weaken the walls. And then eventually, at some particular time, there's going to be a hole that forms, right? We're going to assume it's like a uniform hole. So that means that like sand can just basically fall out now of this. So we're going to have some, I guess I'll call it M dot, I don't know, coming out of the system. That's kind of the idea here. So the sand is now going to come out of this box. So the mass is going to change. So now instead of being m naught, I'm going to say minus little m of t, right? And I'm just going to call this entire thing m of t. So it now has a variable mass. So it's not just a constant mass, it's a variable mass. And we're going to want to analyze what kind of motion comes from this, basically. That's the idea. So first thing to think about is the physics of the situation, right? Initially, the box is going to go upward. That's the first kind of thought here. And you might be asking why. Well, the reason why is because we have, once again, the gravitational force, right? Capital M of t times d, right? Which is, I'm going to say, is this particular function. This is an arbitrary kind of relationship here. But I'm going to say it's m naught, the initial mass, right? Which is the box plus the sand minus little m of t times g. But this is changing. It's decreasing, right? It's decreasing function, which means that the force is decreasing, which means that in order to maintain equilibrium, right, in order to maintain that equilibrium state, the spring here, this, is going to have a restoring force, right? And that restoring force basically is always trying to get the spring back to equilibrium. That's the goal. That's the idea. So it's going to move upward, basically. The gravitational force decreases. The spring force is going to want to kind of counteract that. So it's going to move up. Okay, so what we're going to do is we're going to do a free body diagram of this particular situation, and then try to derive a equation of motion. So that's the idea. So I'm going to take my box here, and I'm going to write it as a dot, right? And that's an important assumption, I will say. If I can just, it's not a rigid body or something, right? We're going to assume that, say, the spring and the damper act along, say, like the centroid, I guess, of this particular box here. So even though I've drawn them apart, they're really acting in the same spot. So there's no like applied torques or anything happening here. It's just simply motion in one dimension, and I can model it with particle motion. That's the idea. Okay, so we know that going downward, of course, is going to be capital M of t times g, right? The weight of the object. And then I know that if it's going to go upward, that's the thought, it's going to go upward. That means that since it's displacing upward, I'm going to call it displacement x, right? That means that my velocity is also upward, right? So I guess I'll call it a vector. So my velocity is going to be upward, which means that the damping, right? The damper is going to exert a force onto the box as well, but that's going to be downward. That's an important thing to know. So this is going to be mu times v, right? It always opposes the velocity term, so it's going to go downward. And then upward is the spring force still. This is going to be k times L minus x. Now that minus x is very important because it's not just going to be, so this is going to be equal to KL minus KX. That's the idea. So it's the original, you can think of this as the original spring force, right, in equilibrium here, me KL, minus KX, right, minus because it's displacing, but the spring is going to be pushing down on it, right, it's going to be pushing it down. It's going to be, wants to return it to equilibrium, it wants to return it to L, basically. So that's going to be slowing it down, basically, that's the idea. So that's the free body diagram of this particular system at this particular time. Now, there is a problem. There is one problem that kind of arises from this is usually what we do is we say the sum of the forces is equal to the mass times the acceleration. This is Newton's second law, or a version of Newton's second law. However, this is not going to be applicable in this particular case because the mass is not constant, right? This particular equation assumes that the mass is constant, and in this case, it's not constant. So I cannot use this equation, actually. So what do? Well, we know that the generalized version of Newton's second law is written like this. It's the sum of the net external forces acting on a body is the rate of change of the object's momentum. That's what Newton's second law actually is. And this makes sense because if I say this is the time derivative of the, right, remember momentum is the mass times the velocity, right? And since I'm only modeling motion in one dimension, one direction, I don't really have to use the vector symbol. So I'm just going to say this is just mv, right? If m is a constant, then it's just ma, right? The derivative of velocity with respect to time is the acceleration. So that agrees to what we had before. But once again, mass is not constant in this case. So we actually are going to have instead the derivative of m of t, v of t, like this, which means we're going to have to use the product rule actually, right? So I have dm dt, v of t, plus dv dt, m of t. Okay, so that's what we actually get instead. So we get this slightly more complicated expression. This is just for the right-hand side, by the way. I haven't even done the sum of forces yet. Now, there's one thing that's important to know here, and that is the physics of the situation, right? This particular equation right here is basically the conservation of momentum. That's what this is. It's saying that the momentum of the system is conserved. That any change in that momentum is equal to a force, is the sum of the forces. And in this particular case, there's actually another term here. Even though the calculus tells us there's only two terms, there's another term from the physics. And that is the relative velocity, so I'm going to call it V, REL, and then dm dt, right? And what this physically means is that since we have, say I have this box like this, and the sand is in here, and it's leaving like this, right? The sand has a momentum, right? These little particles, even though they're small masses, right, they have a momentum. Some little m, say s for the sand, times v s, right? So this is also leaving, this is leaving the system, right? So we have to consider the velocity. Now this vs is the velocity of the sand, but the momentum from the system of like from the body is going to be the relative velocity, which basically is just the velocity of the body minus the velocity of the sand. Yeah, dmt. I think it might be in the other direction actually. Maybe it's vs minus vb. I think it is vs minus vb actually. I might have written that incorrectly. Yeah. So this is just saying that as the particles are leaving, right, the momentum is only relative to the body, because the body is like relative to the particle, the frame that it's coming from. It's once again, it's a physics sort of problem here. But the reason this arises, if you say have a system, maybe like a rocket, right? If I have a rocket, right, we don't have that in this case, but if we did, you're going to be thrusting, right? The idea is that you're pushing out these particles at a very high velocity, right? Which means that this momentum here is very, very high, which means the relative velocity is very, very high. But in this particular case, we're going to actually assume that this term right here is going to be 0. And that's because we're assuming that the sand is just kind of falling out of the box. So we're not forcing it out with some very high forcing, very high force, right? We're not thrusting it out. It's just kind of falling out. So this term is going to be 0. And it's going to simplify some of the equations. Even though it's going to be a little more complicated than normal, this is going to simplify it a little bit more to allow us to solve some things better. So that's an assumption we make. It might sound like a crazy assumption, but it's not too bad, considering the sand just kind of falling out. So that's kind of the physics of the situation kind of taken care of. Now let's continue with the derivation here. Okay, so on the left-hand side, I'm going to do this is our FBD, right? I'm going to do the sum of the forces. So we're going to define up as the positive direction. So my displacement upward is going to be positive. So I'm going to have k times L minus x minus mu times v minus capital M of t times g. We're kind of running out of space there. Equals this. So this actually is going to be my equation of motion, right? Now I'm going to simplify this a little bit. I'm going to do some algebra, and I'm going to skip all that. But what I'm going to use is this M of t. I'm going to write this as m naught, so the initial mass minus little m of t, right? You know, the velocity is the time derivative of position, or the time derivative of the displacement. And that's pretty much it, actually. We'll have dv dt, which is going to be the second derivative of this, second derivative of position. Yeah, so I'm going to use all these particular relationships, and I'm just going to basically solve down and get some expression. So my equation of motion that I get for this particular system is this. So I get m naught minus m of t times the second derivative of x with respect to time plus mu minus dm dt times dx dt plus kx minus m of tg equals 0. Okay, so I get this. So notice, just by looking at this equation, we see that we actually have two unknown functions and their derivatives, right? We have m, which is unknown, dm dt, which is of course unknown, and then we also have dx, or the second derivative of x with respect to time, dx dt, and x here. So I have two unknown functions and like combinations of their derivatives. So it's relatively complicated, pretty complicated. What I'm going to do is, right, we can't solve this. There's a free variable, I guess, or a free function, I guess you could think of it as. I can't solve this in its formulation right now. So what I'm going to do is I'm going to split it into two cases. So I'm going to do case 1. I'm going to call it the constant velocity assumption. So constant velocity. And then case 2 is going to be, what's it going to be? It's going to be a defined mass function. So in one of these, I'm going to be given one of the functions and then solve for the other. That's the idea. So here I'm going to be given the position function, the velocity function, the acceleration function, and I'm going to solve for m of t. That's the goal for this one. And then for the other one, I'm doing the opposite, right? I'm going to be given m, and I'm going to find x. That's kind of the idea. Okay, so let's evaluate case 1. So I do 1. So I'm going to say constant velocity, right? That's a constant velocity upwards, right? Because we know it's going to go up from this original idea here. So what I'm going to say is it's going to keep going up. And the goal is to find what mass flow rate out of this box will allow for the motion to just simply go upward at a constant velocity. That's what I want to solve. Okay, so mathematically that means that my acceleration is equal to 0, right? And I also have my velocity is constant, dx dt is v, I'm going to call it v naught, right? And then I can actually solve for the position, right? Right, if I integrate both sides, that's the idea, dx dt, like this. Okay. That means that x of t is going to be v naught t plus c. But my initial displacement is 0. So x of 0 is 0, right? So this is just 0. The c is 0. So it's just v naught times t. Okay, so when I use this, I'm going to plug this into this equation right here, right? So it's going upward at constant velocity. I have all these things I know is true. So now I'm going to get the following. I'm going to rearrange it a little bit algebraically, but so I get dm dt plus g over v naught m of t equals mu plus kt equals kt. Okay, so I want to solve for m, right? And this, we actually notice, is a particular form of differential equation that we know actually how to solve. This is a linear differential equation, right? It's a first order linear, first order linear, right? And it's written in the form like y prime plus, say, p of t, y equals q of t. It's in this particular form. We know how to solve this analytically using the integrating factor method. That's what I'm going to use. Now I'm going to spare you the details because it's quite messy. There's an integration by parts on this side here, and there's, yeah. So I'm just gonna, if doing that, I guess I'll write the, so rho of t, I usually call it mu in this class, but since I have mu here, I'm not gonna call my integrating factor that. So I'm gonna call it rho is e to the integral of p of t dt. So that in this case, it's gonna be e to the integral of this particular term, which is g over v naught dt. Okay, so I multiply both sides by that particular integrating factor like this, multiply both sides. And then I rewrite the left-hand side, right, as this, the derivative of, I'll call it, I guess rho of t times m equals this times rho of t. And then I can integrate both sides. And then I can eventually solve. So once again, there is going to be a PDF attached to this video. If you want to look at all the details, you can. But yeah, it's pretty messy. But in the end, I'm going to get m of t is equal to this particular function here. Give me a sec. It's going to be this. So v naught over G times mu plus KT minus KB naught squared over G squared, right? A lot of these are just, there's a lot of variables, but once again, most of these are just numbers. Like I determine a lot of these coefficients. The only thing that's changing here is T. Mu over G e to the minus GT over V naught. Okay. So we see that m of t, in order for this to leave at a constant, or in order for this to move upward at a constant velocity, is on the order of some combination of a linear function, this is a t, and an exponential function, which is kind of interesting. And also one thing that's important to note is that this function must always be greater than 0, right? Because my total mass function m of t is m naught minus m of t, right? And this total mass function can't be negative, right? It has to be greater than 0, strictly greater than 0, because we're going to assume that the box actually, like the walls of the box, have some mass, right? So this is greater than 0. So that of course means that m of t must be greater than 0, right? But not greater than m naught. So this function is always greater than 0. And this agrees with that, right? Even if these particular right, it's not always negative or something, right? We get something that makes sense. And then the linear part and the exponential part is going to depend on what my I think there should be a parenthesis there. I might have forgot that. But it's going to depend on what my parameters are, whether it's more linear or more exponential, right? Things like that. But overall, this is what we get. And this particular term here, I will mention, this was actually a C when you do the integration. But we can use an initial condition, which is kind of trivial, is that m of 0 is 0. The initial mass loss is going to be 0 at t equals 0. So then I can solve for C very easily using that relationship. Anyway, so I get this particular function here. And let's look at some graphs of it. So I have some plots here of this particular function with just these, once again, these are kind of arbitrary, these numbers here. But we see something that makes sense, right? We get a linear function, right? Asymptotically linear is what I would call this particular function. And then it's also has some exponential term kind of added to it here. And we see the same thing here. We actually have an opposite kind of situation here. So it's once again asymptotically linear and has this exponential term there. One thing to note, once again, is that the m of t, little m of t, cannot be greater than m naught, because then that means that mass is negative, which is not true, physically not true. So that's why we have this dotted line here at this, for say m naught being 10. We have the dotted line at 10. And that's why the solution curve abruptly stops, because it's no longer defined. And we can also understand this asymptotically linear behavior just by looking at the equation, right? If I think about taking the limit as t goes to infinity, right? And this t goes to infinity is a little misleading because this function is not defined for all t, right? But in general, if I did a limiting process, this particular exponential is a decaying exponential. So this just goes to 0, right? And I get something of here, right here, which is on the order of t, right? It's a linear function. So everything kind of makes sense. So that's what we get here, which isn't the most interesting thing in the world, especially the limiting part. Like it comes out at a linear rate. It's not that interesting. But it is kind of interesting that at the very beginning of the motion, it has to have some sort of exponential terms there. Also, one thing to note is that the PDF that'll be attached to this video has the full derivation of all the stuff that I have here. So there's not just like coming out of thin air. There is a derivation. And also there is code, there's Python code for this particular thing. So if you want to plug in other parameters, you can. You can see all the solution curves if you want. So that'll be linked as well. But now let's look at case 2. Case 2 is a little bit more complicated, but it's more interesting. So for case 2, I'm going to say I have a defined mass function. What that means is that I just know what m of t is, right? I'm going to say that dm dt, so the rate of mass flow out of the hole is going to be gamma, so it's going to be constant. Right, this of course means that my m of t is going to be gamma times t plus some initial gamma naught. But once again, m of 0 is 0, right? So that just means that m of t is going to be gamma times t, right? This is just 0, essentially. Okay, so I have a defined mass function now. So now I can take this, so I have this, and I have this. And I'm going to plug that into the equation up here. So where was it? Right here. So in the first case, right, we were substituting for this, this, and this. Now I'm substituting for this, this, and that. Okay. And once again, the algebra gets it actually isn't that messy this time, but I'm going to skip a few steps here. So I'm going to say that means that I get this equation here. I'm going to write it like this. So I have m naught minus gamma t, right? So we take that in. Second derivative x time plus mu minus gamma dx dt plus kx minus gamma tg equals 0. Okay, so right, we want to solve for x. So x is here basically in all these. Right, there's x, and then there's the first root of x and the second root of x. So this is a second order linear. It's actually a linear equation, right? There's no like nothing like squared like this. It's a linear combination of the derivatives of x, but it also has a non-homogeneous part. So there's this thing here, right? There's a t there, but it's actually linear. But the main problem with this particular like equation, why it's complicated to model, is this right here. That's a non-constant coefficient, as we call this. So that's gonna make this a little more complicated to model. So it's not, we can't solve it using traditional methods. But before I go and do an interesting solution, I'm gonna find an equilibrium solution, which just means that I want to set the motion. Is there a stable solution? That's basically what I want to see. So I don't want to spend all this computation time trying to solve this when there's not even really a good stable solution in the first place, right? So I'm going to find the stable solution first, like if one exists, and if one does exist, then I'm going to kind of try to find what the motion looks like before it kind of reaches that stable point. So to find the equilibrium solution, I set dx dt to 0. That's the goal. So this equals 0. So basically no velocity. It's just staying in place essentially. This means, of course, that the second derivative of the acceleration is going to be 0, right? So basically, this is 0 and this is 0. And I can solve for x, right? This right here means that x is going to be a linear function. I'm going to write like this, right? So I'm going to call this x sub eq, right? So this is actually telling us that our displacement is a constant function, linear function, constant linear function. Which means that even though my velocity is 0, right, I'm not like moving with a velocity. The position or the displacement of the spring of the box is like at a line. It's changing actually, like it's moving. It's still moving actually, but with a 0 velocity, which is kind of interesting. So if I wanted to plot it like this, it looked like this, right? It'd be I guess I could do a dotted line maybe. Right, this is not the solution curve, but like say as time goes on, we're going to eventually approach a line, which makes sense because as it goes up, right, or down, right, it's losing mass, right? So usually in the normal case, right, if it's normal spring without any sort of changing mass, we just have an equilibrium solution like this, right? And usually we like oscillate about it like this, right? But here it's angled because like at a particular slope because we have mass loss. So that's kind of an interesting thing that we see from this particular relationship here. Okay, but we still have not solved for x. So how am I going to solve for x? Well, what I'm going to do, and I'm going to get rid of these x's so you can kind of see it a little bit better. What I'm going to do, since it's a non-constant, non-homogeneous equation, I'm going to use a power series solution. That's the idea. What that means is I'm going to say I'm going to let x of t equal a power series. So I'm going to say I equals 0 to infinity ai t to the I. So we don't know what AI is. That's the problem, right? If I knew what AI was, then I'm kind of done, right? I know the answer is, but I don't know what AI is. That's the problem. So the goal, so I'm changing, instead of trying to solve for X, I want to solve for AI, right? Which is, AI is a sequence, right? It's just a sequence defined by some index I. It's just some number. And that's going to tell me the coefficient to multiply by t, right? Because this is going to be like a0 plus a1 times t plus a2 times t squared plus blah, 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 right? So the goal, I'm going to change kind of, even though I don't really know how to solve for x, and I don't really know how to solve for AI either, But I'm gonna test my luck, see if I can find AI, and then I can potentially write my x as a solution. And one thing that is kind of like a technical thing to understand is that I'm expanding about t equals 0, right? I'm doing a power series expansion about t equals 0, which makes sense, right? I don't really want to do it about, say, like t equals -1 or something. I want to do it about t equals 0. I want to see the motion of the whole thing over time. Okay, so I say my solution is a power series. That's the idea here. And I can actually utilize this in my equation up here to solve for AI. That's the goal. I want to solve these coefficients, right? If I can find some relationship, right? If it's usually we call it a recurrence relationship. So let's say if I had like an plus 1 equals like an plus 1 or something. That's not a good example. Maybe an plus 2. This means that the next term of the sequence is based on the one before it plus something, right? And you might have seen sequences before, say like Fibonacci sequence, like 1 1, and then I add the 2, right? And then 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, right? Blah blah blah. Right, this is a sequence, right? That's defined in terms of actually the first two, like the two terms before the current one. So that's kind of, if I can find some sort of recurrence relation, then I can be kind of satisfied with my solution here for x. Okay, so what I'm going to do is I'm going to start differentiating this. So differentiating a power series is very, very easy to do because it's a polynomial function at the end of the day. So I can actually differentiate term by term. That's the idea. So it ends up just being I times AI t to the I minus 1, right? And if I wrote it out, this goes to 0, and I just get A1 plus 2A2t plus blah, 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 right? Up to. And this keeps going. Yeah, okay, it keeps going. And same thing for x double prime. So x double prime, right? I do the same kind of idea here. So I'll write that out as well. So I get I minus 1 times I, and then AI t to the I minus 2 equals 2A2 plus blah, blah. Okay, so that's the idea here. And now I'm going to take these and I'm going to start plugging them into my equation here. So I'm going to take x, x, plug it in up here, take x prime, plug it in there, and then x double prime, plug it in there. But before I do that, I can actually get a few coefficients actually with just based on what I know right now, right? Because x of t is going to be a0 plus a1t plus a2t squared. So it means that x of 0, right, is going to equal a naught, right? And I know my initial position is actually 0, right? It's really displacement, but in any case, it's 0. So I can actually solve for a0. So I solve for one coefficient. Great. I need to solve for n more, but I did solve for one. And then same thing with x prime of 0, right? I actually find this is a1, which I know is v naught, my initial velocity. Okay, so that's the idea. So I want to solve for this. So I found two coefficients, but I need a lot more. I need infinitely more, actually. So that's why I'm going to end up substituting these into this equation here. Now I'm gonna skip a few steps here. Once again, you can look at the PDF if you would like to see all of the mess. But the idea is once I plug this in here, and I'm actually gonna write this out here. Let's see here. Yeah, I'll write this one out. So I'm gonna start. So you plug in the particular relationships that we got for x double prime, right? At x prime. And then you're going to plug those in. You're going to get a big mass, basically, of equations. And then you're going to start expanding out the sums. That's the idea. So I actually end up re-indexing a lot of these sums. And re-index just means like I just kind of change the indexing variable so that they all start the same, just to make it a little bit nicer. Once again, I'm running out this big ugly thing. So, but anyway, you re-index all the sums, and then you kind of simplify some things, and you're going to start expanding out the ideas. You start expanding out all your terms. So, wow, that's a lot to write here. Sorry. Mu minus gamma n equals 0 to infinity. I think. Oh no, this is 1. N plus 1. An plus 1. T to the n plus, almost there, plus k, n equals 1, n, a n t n equals g gamma t. Okay. Oh, that was a lot. Okay, so basically you start expanding out all these sums, right? And you start seeing that the left-hand side of the equation, because it's a non-homogeneous term, right, is from here. So I basically just move this to the right-hand side. So I say this is gamma gt, right? I just move it over, and I use all of this is equal to that. So in order for this to be true, all the coefficients at each order of t have to be the same. That's the idea, right? So if I expand out all the constant terms, right, which these are all constants, if you notice, there's no t's there. They all have to be equal to 0 because there's no constant term here. This is like 0 times t. Okay, it's all equal to 0. So that means I can actually solve for a2, right? So I know that this particular combination of coefficients has to be equal to 0. So it means I can actually get a2 from this. So a2 is going to be, once again, just algebra. Gamma minus mu v naught divided by 2 m naught. Okay, so that's what a2 is. So now I have 3 coefficients or 2? Yeah, 3 coefficients. I have a0, a1, and a2. Great. And then I'm going to expand out one more term, right? If I went one more term, I'm going to get a bunch of terms of t, right? So I have like, say, like c1t plus c2t plus blah, blah, blah. Like I don't know, cnt, right? And this must be equal to gamma g times t, right? So once again, I can just equate the coefficients. So that means that c1 plus c2 plus blah, 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 cn equals gamma g. So that gives me another relationship to find the coefficients of the next term. So say like a3. So I could get a3 equals, now a3 is actually really nasty, and I'm just going to leave it off for now, but it is equal to something. Okay, now this once in principle goes on forever. Now there's one key idea that happens is as I increase n, right? Because for n equals 0, it's a constant term, so it's equal to 0. For n equal 1, I have a t term, so it's equal to gamma times g. And then for any n greater than or equal to 2, it's going to equal to 0. The sum of all these coefficients is equal to 0, right? Because there's no non-homogeneous term there. There's not like a, say, I don't know, a ct squared here for my forcing function. There's nothing there. It's all 0. So all those terms have to be equal to 0. And that means I can actually define a recurrence relationship between, we have an plus 2 here, an plus 1 here and here, and then an, right? So now I actually define a recurrence relationship, and I know the first 4 coefficients, actually. And so that means that I can actually define the entire recurrence relationship for any n, which is really interesting. So I'm going to write out an plus 2 in terms of n plus 1 and an. So I get this particular thing. So once again, the coefficients with order t to the n when n is greater than 2 have to be 0 in order to satisfy the equation of motion that I wrote earlier. And when you do that, you're going to get this, which is once again quite messy. So this is n greater than or equal to 2. Okay, so I get this. So an plus 2, the nth plus second term depends on the term before it and then the other term before it, essentially, was what this is saying. So if I wanted to find a4, right, I know, yeah, a4 is going to be some combination of, right, so this means n is 2, right, n is 2. So you plug in n equals 2 here, and then n equals 2 here. I know what a3 is, right, in principle. So this is a3, right, minus k times a2 divided by this, right? So then I can keep going. It just keeps going. So I can define all these coefficients, which means I can define an. So I actually found an. So I did not find x. I found an. But I know that x is going to be a power series with an as its sequence, right? So that means I can basically approximate, right, x, which is, I'll change it to n. The indexing variable doesn't really matter here. But this is my solution, right? I actually found an. I found all the coefficients for any n, and I can write the solution as this. So that's the idea of a power series solution. So that's what we can do in this particular case, even though it's the details are quite nasty. The idea is quite simple, actually. And so yeah, so that's the idea. I can write this as a power series solution, and then now I use Python in this particular example to generate the plots that you're about to see. So I just go up to some number of terms. I think I have n equal to capital the number of terms equal like 150 or something. So I have quite a few terms here to see. So you get a decent approximation of your function x. So let's look at some solution curves. So if I look here, here's my first solution curve that I have. Once again, all these parameters are kind of arbitrary. The most important parameters here, I would say, is your initial position, which is always going to be 0, by the way. We kind of assume that to find the coefficients. Yeah, the initial position is 0, or initial displacement is 0. And then the velocity. So this is the initial velocity. So we're saying that our initial box is actually going upwards at a velocity of 1. Whatever units this is, it doesn't really matter the units here. So that's what's happening. So I'm saying I like pushed it up basically from equilibrium. This is what's going to result with a constant mass leaving the system. So it's going to oscillate up, right? And it has this really interesting, so it's a sinusoidal kind of pattern, but it's along this asymptotic line that we found earlier, right? The equilibrium solution. And so that's kind of what we see here. At the end here, you're going to see some noise, right? And once again, the code is in the PDF. If you want to actually put this into Python yourself and plug in some numbers, you're going to see a lot of noise terms. So it might like look like it diverges, right? Once again, it's power series solution. So it's not going to be defined for all t. There's going to be some range to this where you're going to run out of values basically, and it's going to just die because it's a polynomial at the end of the day. So that's what that kind of, so the actual motion doesn't look like that. It's actually like, it's a smooth line, right? And same thing for another plot here. This one's a little bit not as interesting because both initial conditions are 0. So it starts at rest, and I kind of just let it sit there. And it's going to oscillate a little bit because the mass is changing, but it's nothing super crazy. But this makes sense. I think it's important that you kind of always do a sanity check, right? That all of this math I did actually does make sense to what it's modeling in the real world. And then another one here, I just have, instead of it going up, it's going down. So the initial velocity is going to be negative. And of course, we have a displacement that is negative, which makes sense. And once again, we have a little bit of noise here from that power series term. But that is kind of the overall motion of this particular thing. It's just kind of some oscillatory, right? If I increase mu really, really high, it's going to be like an overdamped case. So I might kind of have something like this and then kind of go out like this and kind of asymptotically go along that line there. But in general, that's kind of satisfied with that solution while it's not defined for all t, right? And that's actually true in general because once again, there's a mass function, right? It's m of t, right? Or sorry, m naught, yeah, m naught minus little m of t equals a capital M of t. Sorry, the handwriting was kind of bad there. Right? This is only defined when this is non-zero, right? So once we run out of mass, essentially, is when x is no longer defined, and it just stops. Basically, is the idea. So it's not defined for all t anyway, so it's not really a huge deal that we have those noise terms from the power series solution. So yeah, that was kind of the project in general. So once again, returning to the start, we kind of explored a model here. So we took a basic oscillator and we added one particular thing, which is that it has a variable mass now instead of a constant mass. And then we derived the equation of motion for it, and we solved it. Once again, solve kind of depends on how you define the word solve. And then we interpreted solutions. So that's kind of a summary of the honors project that I did. Once again, if you want to look at the code, it is in the PDF. And of course, a formal write-up of all the coefficients and all the algebra, if you'd like to see that, is also in there. So yeah, thank you for watching.